How was your weekend? Grand, huh? It was my favorite type. Saturday, I didn't even get out of my pajamas. It was great. I did a lot Friday and Sunday, but, you know, oh well. Let's see, close a few things. I'm working on the last bit of writing your test. I'm sure you're real excited, right? All right. Today we're going to review, and I hope you guys have lots of questions so that I can help you feel better. Okay, now that's ready in case I ask you some questions on this demonstration. So I'm going to start with questions. We got one already. Go. Oh, even better. You heard there was a star that propelled a black hole through space? I haven't heard this, but I don't. Huh? Do you read it online or?
No, it's been a place my friend was telling me. I think it was actually a binary star set that sent a black hole into space. I don't know if that's true.
Binary star is propelling a black hole. Well, I haven't heard about that one specifically, but let's see. In my mind, if a black hole, if you don't know, is extremely, extremely massive. It has a lot of mass. Thus, it has a lot of gravitational attraction. It sucks everything in. Even light, if it gets too close, can't escape. No matter how, well, I was going to say no matter how fast it's going, but it is going fast.
Yeah, and where does it end?
It doesn't. Where does it end? It doesn't. In a black hole, it just keeps sucking things in and grows, gains more mass. Whatever it pulls in, it adds that mass to its, increases its gravitational attraction, and has even more pull on other objects. So its pull, we can analogy the Earth like a black hole because it's really massive compared to us, and it influences us. So usually a black hole would influence neighboring celestial objects. That's what we notice because of Newton's second law. They have less mass, so their acceleration, they're affected more. However, we do affect the Earth, don't we? Because of our mass, Newton's third law. And so, any object can exert and have an effect on a black hole. It just might be really small. Thus, what I'm getting at is there could be an effect, and you might have heard of the slingshot effect, maybe from Star Trek, where if something has momentum, it's already moving, inertia in motion, kind of like the chain coming out of the cup. Once it starts moving, if something is trying to influence it, it has to slow it down first and then turn it back around, like when something bounces. It hits the table. This exerts a force on the ball to slow it down and change its momentum to zero. But then it rebounds, and the table continues to push on it and accelerate it back up to change its momentum even more. And if something's kind of going around an object, it's going to bend towards it because it's attracted. But now we have our components. So I'm trying to review here too, see how I do that. So if it has momentum in that direction, and then this body exerts a force on it in that direction, it's going to move not only that way or this way, but in a component of that. And so it goes around. And as it goes around, you can increase its speed. Maybe it's something like that. If you find it, you can send me a link. I'll read up and see if I can understand it more. Thanks. Next.
So going along with that, does light have mass?
Does light have mass? Deep question. I was going to say short answer. I don't know whether to tell you short answer is yes or no. In my mind, yes, absolutely. In scientists' minds, no. Technically, it has no rest mass, which means if it were to stop moving, it would no longer have momentum, It would no longer have kinetic energy because they're both associated with motion. It would no longer have mass, according to scientists in the theory of relativity. But while it's moving, it does have some mass, this inertia. It's very, 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 very small. But yes. You first.
Yeah, well, that's because of energy. Energy has mass, so light should then have mass as well.
Yes, energy has mass. Mass is energy. One of Einstein's popular formulas, E equals mc squared. Energy, mass, the velocity for light, the speed of light squared. Thus, its matter, what it's made out of, relates to energy. If you could completely convert mass to energy, it would be this relationship. But again, this applies when it's moving. So they claim that if it were to stop, it would, in a sense, cease to exist, have no mass. Yes?
Have been achieved though during if they supercool a certain substance and shoot a beam of light through it, it momentarily reduces the velocity of that beam of light so they can look at it. And then as it exits the other side of this, I can't remember the name of the substance.
Are you thinking of Bose-Einstein condensate?
Possibly.
They do use lasers and super cool things. We're going to learn in 3 or 4 more chapters. Energy. Everything has energy. And if you have a temperature, that's a measure of your internal energy and how fast the atoms and molecules are moving. If you cool something down, they move around less. They have less kinetic energy. So they're moving slower. And so in theory, if you got it cold enough, they would stop altogether. We call that absolute zero. But still energy's, conserved. And they can use lasers to stop them with momentum. It's a collision. If you got a particle moving this way with some momentum, and you hit it with a laser beam that has momentum, do you remember what happens if, for simplicity's sake, if this is the same mass as this, and they're coming at the same speed, what will happen when they hit? So it's like 2 same-sized balls going the same speed. They run into each other. What will happen? Transfer momentum and what? Well, let's do one then, because that just might be on the test. Okay, an aside. Well, let's do that then. Let's say we got one going mv to the right and one mv to the left. Same mass, same speed. Let's say to the right is positive. That makes this one positive and that one negative. They are vectors because of that velocity. What's the total momentum before the collision? Plus mv and minus mv. 0. So what's the total momentum after the collision? 0. Right. So they're going to hit. And that one they'll probably bounce off each other. And this one will now be negative, and this one positive. And you see that they'll still add up to 0? So they'll be going at the same speed in opposite directions they were coming in at. They do something with Doppler effect and shifting, or when my gist with this is they're using laser beams coming in at specific speeds and momentums, and you can slow things down and change their momentum, get it to stop. Then maybe it starts going another way, and they do that. And yeah, a Bose-Einstein condensate is essentially this little bunch of objects, particles, atoms, in a well that have essentially stopped moving. Yeah, it's still absolute 0. Theoretically, you lose all motion. But nobody's ever achieved that yet. Other review questions?
I read an article some time ago where they were able to determine that ice is still moving, particles within the ice is still particles in ice are still moving. So absolute zero has to be colder than the temperature of ice. So we know that even ice doesn't reach absolute zero, that it has to be colder.
Absolute zero is extreme, much colder than ice. Yes. So relatively, ice is pretty hot. So yes, its particles are moving around.
Right. So where can we actually see a good example of absolute zero? Does it even really exist, or is it just a theoretical concept?
Nobody has achieved absolute zero yet. They've gotten close with a Bose-Einstein condensate, or things out in space sometimes can be pretty close. They're like very slightly above absolute zero. Takes a little longer. Good? Okay. Yes?
I have a question. After collision, the tubule will move back or stop the tubule?
I'm glad you asked, because while he was asking that, I thought I would do another example. If it's an elastic collision, then they bounce off each other, and this is what happens. What if it was inelastic and they stuck together? What would happen? The momentum's going the same way? Whether they keep going or bounce off each other, the momentum will still keep it going. But let's look at the total momentum. It is zero in this case. So whether they bounce off like this or stick, the total has to be zero. If they stick together, because they're two pieces of clay, let's say, which way are they moving? We now have 2m moving at some velocity, and that's got to be zero, total momentum. So the velocity is zero. They stop moving in that case. If, as your gut should tell you, this were 5m, it's 5 times as massive. Now your gut tells you, point. Which direction do you think they will be moving after the collision? Point. Yeah, most of you are pointing to the right. And we can know exactly how much. Because now after the collision, it would be 5m plus 1m. Let me write that out. Moving at some velocity. I don't like where that was heading, so I'm just backing up so that I write it correctly. Oh, because we start different. That's my problem. It's a new problem, so I have to figure out what's the total momentum before the collision. It's no longer zero, is it? We have plus, 5m going plus v plus m going negative v equals the total. Do you see that before the collision? 5m coming in this way, 1m coming back this way. That is 4m, right? For mv, correct? I lost anybody? So that's what the total momentum is before. That's what it has to be after. So now we can go. We got the 5m combined with the 1m going at some final velocity. And it's got to be the same total. So let's rewrite that one. 6m v is 4 mv. Divide everything by m and v, they go away. So I just messed up again, didn't I? What am I doing? Why am I a dork? Where am I a dork? The 6 came from there. Oh. These, that's what I get for making it up on the fly and doing it. Okay. Let's call this initial velocity. That makes more sense. That's what they're initially moving at. This is not the same v. That's what we're trying to figure out. So I should have behaved and labeled them. Those are not the same v. Does that make sense? It obviously threw me off for a moment. So your gut is telling you, yeah, it looks like it's going to the right because the one coming from the left is bigger. But I wanted to work this through and so you can figure out exactly how fast they'd be going together. So now the m's cancel. And that final velocity is 6 or 1.5 v. And it came out to be positive. Good thing, it matches our gut. So if they stick together, they're moving to the right with a velocity 1.5 times greater than they came in at for that specific case. Before I answer, since it wasn't as smooth as it could have been, again, total momentum before, no matter what the situation is, has got to equal the total momentum after. And if you label initial and final, you don't get messed up like I just did. And you can figure out exactly how fast things are going to be going. And in which direction, even if it's not obvious. Yes?
I think there is something wrong with that. The final velocity is 2/3 VF, I think. Oh, VO.
2/3? Correct?
No.
So I wrote this wrong?
Because over there, yeah, and there is 4N VO, not 4N VF.
Oh, you are correct.
So the total momentum is 4N VO.
Oh! Thank you. I believe you're correct. And now that I've befuddled everybody, let's start over, shall we? Now, yes, I'm embarrassed. Yes, I'm sorry. However, I always liked when my teacher messed up. I don't know if this is any consolation to you, because I like to see how they work through things. Because when I'm working through them, it doesn't come easy, and it seemed like I never got it right the first time. So I like seeing how they thought. So at least I didn't feel as dorky when I was trying to do it. And again, I'm sorry. Let's do it again. So they're coming in before the collision. We'll call this initial velocity, and they're the same, just opposite directions. So his momentum is the one on the left, 5mv, initial. The one on the right is going the other way, so it's mv negative. So the total momentum before the collision is a positive 4m v initial. Okay, now let's do after. Now that I got my subscripts. Okay. We're going to have them stick together. And what is that final velocity? Well, they're going to be a 5m here and an m there, so a total of 6. And will they be moving? Well, we already figured out, yeah, to the right. But if you didn't know, and if they're not moving, 0, it would come out to be 0. Let's find out. So after is 6m moving with some final velocity. And that's got to equal the total that it was before. If you wanted an actual number, you would need to know the velocity value, yes. I haven't given it to you, so I'm doing it generically. So then solving this, divide by m. I want VF. That's 4V over 6. Bring the 6 under and over, which is 2/3 V naught, and it's still positive. You can thank your brave student for catching me on it. And yes, the final velocity, still to the right, 2/3 of whatever the original incoming was of the two. Well, good. Well, we've worked conservation of momentum. Other questions? Everybody clear on that now? I've reconciled myself from confusing you initially? Okay. All right, other things. Oh, yes? Is energy conserved in an elastic collision? Total energy is always conserved, period. In an inelastic collision, yeah, if these two balls of clay stick together, some of that kinetic energy they had is going to be converted to thermal energy. So a lot of people say kinetic energy is not conserved in an inelastic collision. That's true. Thus, you couldn't play this same game doing conservation of kinetic energy in this instance, because it doesn't include that little bit of thermal energy that would escape. If, I said, I don't know, making it up, 1 joule went away as thermal energy, then you could solve it, because the remaining kinetic energy is still conserved. So whatever kinetic energy it has before will have to equal what it is total after. So in that case, it'd be like the kinetic energy before will equal the kinetic energy after plus whatever work was done by friction, to turn it into thermal energy. Does that make sense? So, thoughts. If I said it was inelastic just like that and gave you this and this, the kinetic energy before and after, and they weren't the same, then you'd know exactly how much that was, or vice versa. Okay, I got one. How much work is being done by me on this ball? Let's see, we could even know. This is 124 grams. And we'll give you another value that you might be wondering. Here's a meter. Work is mass times distance? No. So we're going to lift it 1 meter. Work is force times distance, Brian. So let's see, how much work did I just do on it? What force do I have to exert on it? Bare minimum. Yeah, mass times gravity. That's the Newton's second law. .124? Oh, you already figured it out? Sort of. Just a second. And the distance is 1. And I purposely tried not to give you problems on the homework that weren't already in standard units. Thus, I'm not trying to trick you here. This is .124 kilograms, and that's the standard unit we've been using for mass. So I'm going to put that one in so that these come out in the units we're used to. So 0.124 kilograms times, we'll just use 10 meters per second squared. That's kilogram. And that comes out to be 1.24 joules. Now, did I do that one right? So that's the amount of work I do on this specific ball to raise it 1 meter. How much energy does it now have up here? 1.24 joules. Good. How much kinetic energy does it have right before it strikes the table? 1.24 joules. How fast is it going right before it hits the table? So basically, I did work to lift it. That changed its energy. We gave it gravitational potential energy at the top. And then that was converted to kinetic energy at the bottom. Kinetic energy is 1/2 mv squared. And that's equal to 1.24 joules. So if you plugged in the mass, you would know how fast it's going. Could you guys do that? That's the total energy. So that's the kinetic energy it has right before it hits. Since I gave you the mass in this case, we could figure out exactly how fast the thing's going to be going right before it hits. Thus, you would know its momentum too. Because after you have the velocity times mass, that's momentum. You would then know its change in momentum when it hits the table, right? Because it starts out, it comes in with certain momentum, mv. So you now know the impulse. Just trying to make the connections for you. Impulse was force times time, do you remember? So if I gave you how long the collision took, you could even figure out what the force is between the two. And would that be the force on the ball or the force on the table? You think that force that's making this change once it hits is the force on the ball or the force on the table? Vote for a ball. Another vote for ball. Anybody think it's a table? We'll just knock that out of the way. Well, when they hit, you know this. When they hit, the ball exerts a force on the table. How does the force the table exert back on the ball compare? They're equal and opposite. Newton's third law. So it doesn't matter. It's the force on the ball and the force on the table, right? It's the same amount. They're equal and opposite. So that tells you the force on the ball to slow it down, and it also tells you the force that it's pushing on the table. You solved it?
Yeah. So it's like 4.47 roughly velocity. What would that be in terms of units?
Since we are using standard units, that's why I wanted to switch. You putting that in kilograms? Then velocity will come out in its standard units of meters per second. What'd you get by chance? 4.47 meters per second? So you drop this ball from a meter up. You know how fast it's going now, right before it hits. Other questions, issues, things that have been bugging you? Past homework problems that you didn't figure out? Other lectures, things in the book that you think I didn't explain well? Yeah.
There's that problem homework that a plane is going 40 meters per second and it drops at a 50 meter altitude right when it drops.
Yeah, you got a plane. Whee! Beautiful, I know. Moving along. And it drops something out. And it asks where it lands. What'd you put?
I tried a few different answers. Didn't give it to me. I tried to figure it out, it just wouldn't work.
Anybody else want to add that thinks they did figure it out? Yeah.
It falls where the plane is further along its path. It's like if this plane is then 50 meters ahead, the package will land 50 meters ahead.
So if the plane goes 50 meters ahead, this will land 50 meters ahead too. So it'll still be underneath it? Another vote for right under the plane. Well, let's see. The triangle when it makes. While it's still on the airplane, what's its velocity?
40 meters per second.
Yeah, the same. So they're moving together. It's like my cart on the rail. That I push the cart along with the ball inside of it. And then at some point the ball shot, but it still had a horizontal velocity. So it's plane and package. So when the package gets dropped, it still has that horizontal velocity. It just now also has a vertical velocity because it's being accelerated downward at 9.8 meters per second squared. So like our monkey chute, cougar chute, the plane will go along. It'll be here, and here, and here, and here, because it's going at a constant speed. So the package will be here, and here, and here, and here, horizontally. It's just that it falls also. So in the first second, it might be a little farther down. The second, it's accelerating vertically, so it'll be a little farther down. And this one even more down, and until it runs into the ground. But it'll still be underneath where the plane is moved to. They both have inertia. They both have a horizontal component velocity. So they're moving in sync horizontally. If you draw the vector, I think it's easier to see, yes. This is why at the beginning, more with forces, I emphasized drawing a free body diagram, see what's going on. Sometimes if I'm confused, I just start drawing arrows. Then I can see it. Projectile motion. Whoosh. I thought, oh, yes.
I think the reason I got that problem wrong the first time too is because I was finding it in relation to the ground and not the plane. So I saw like, oh, it says this many meters, that's right. And then I was like, oh, duh, it's going to be right.
Oh, so many meters along the ground. Yeah, because your gut was right. It's going to move forward. It's just that, oh, the plane's moving at the same rate forward. So they're still relative to each other. Yeah. What? Oh, exactly. Figuring out. You could do all that. With your kinematic equations we had. You know, accelerations, velocity times time. This one's 1/2 at squared, following the times. And you can solve the whole thing that way and still agree. But conceptually, I find it a little easier how we just went through it. Okay, I got one. So if we went through the work of me lifting this up. How much work am I doing on it now? Zero. Why? Because I didn't move it. Remember, work's force times distance. It's the force acting in the direction it causes it to move. Well, one, I'm not causing it to move. Remember, work is how you initiate a change in energy. Am I changing its energy any? Not potential, not kinetic. So no, I'm not doing any work. I'm not moving it, displacing it. Zero. Okay? How much work is the table? It's going to roll. How much work is the table doing right now? Zero. How about gravity? Zero. How about gravity? Yeah, it's still zero. Because gravity is trying to make it move which way? Vertically. And even though it's still exerting a force on it, the table's stopping it and it's not moving. So that's just like me doing this. I'm pushing on it, but it's not going anywhere. Earth is pulling on it, it's not going anywhere. I'm pushing on the wall, it's not going anywhere. So, no work. Good. Keep thinking of questions. Should we do a demo? This is a good one.
So no work, no energy?
If there's no work, then there's no change in energy. We haven't changed its potential, its location, or its motion, kinetic. I'm going to attempt to shoot a pencil through a piece of wood. And I want to see what you guys think will happen. So I'll give you the session ID number here. We'll have a vote. 431-076. Okay. I'll try it twice because I have two different pencils. One of them I sharpened and one of them is blunt, unsharpened. And we're going to put it in this pipe. These are number 4, 2H, extra hard. So I put it down in this tube at the end, and I'm going to then close it off and propel it. I'm going to exert a force, see there's good review here, over a certain amount of time. It's like the marshmallow in my pipe. That force is applied until it comes out the end. So it accelerates. It receives an impulse, changes its momentum. I'm going to do it the same each time. Put the one in and then do it, and then the next one. How will their velocities compare when they come out the end? Same. Very good. So they're going to have the same momentum, same kinetic energy, essentially. Slightly less mass, whatever. Then we're going to collide with this piece of wood. And that's going to change its momentum. It's going to make it stop. Will they have the same change in momentum? If they both stop, will they? Yes. Yes, they'll have the same change in momentum. Well, what do you think will happen? That's my question. It's an easy, A or B. Which one do you think will penetrate further through the wood, if at all? The sharpened or the unsharpened? So vote. I'll open the polling. I always like to see what people think. Number 1, number 2. Sharpened or unsharpened? Which one will go through farther? While you're voting, which one should I do first? You want me to do unsharpened first? I'll set it up. That way, save some time while you're still voting. So that's good. We're applying an impulse to change its momentum, to change its motion, give it kinetic energy. It's then going to transfer that momentum and kinetic energy into the piece of wood, which is going to exert a force on it and stop it. Yeah?
Which one are you doing first?
I'm going to do the unsharpened first. What?
The unsharpened doesn't have flat surface at the top?
Yes, the unsharpened does have less surface because it's unsharpened. So it looks like that, where the sharpened looks like, well, you get the idea, that. I guess technically. Yeah. All right, what do we got here? Get your vote in. 5, 4, 3, 2, 1. Okay. Okay, so most of you think the sharpened one. 78% of you think it's going to go through further. So we have the unsharpened in right now. Most of you are going to be unexcited then, I think, according to your votes. All right. Interpreter, I just want you to be watching. This can throw out some splinters. I won't talk so that you can look. 3, 2, 1. Forgot about that. Cool. That one made it this far through and then broke. So now let's try the sharpened in a moment. I grew up in Kansas with tornadoes. And after tornadoes, it was very sad. But I'll admit, one cool, in quotes, thing was finding various objects stuck into other objects. Things you wouldn't think would stick. 2x4s in the sides of buildings. A big carpenter's level stuck in the side of a truck. A tennis shoe stuck in the side. I forgot what that one was stuck in the side of. It was impaled it. All right. Ready? 3, 2, 1. The sharpened one stuck also. It made it through, but it didn't go as far. And that's typical. The sharpened pencil usually does not go through as far. It usually gets about this far and breaks off or doesn't penetrate at all. And sometimes the unsharpened one goes all the way through. That's fun and scary. Why? This one, again, they come in with the same momentum. They both stopped. So they both had the same change in momentum, same impulse. You agree? Thus, That's what happened. The sharpened pencil has a crumple zone. The lead gives way. This is the dominant thing that's going on. Other things are happening, but it crumples like a car that crumples, or an airbag, or a pad, and that increases the time of the collision. Not much, but enough. You see the difference. So the force that the pencil exerted on the wood was less. And the force the wood exerted back on the pencil was less. The pencil didn't go through as far. Didn't break up as much this case either. The unsharpened, it whacks it all at once because it's blunt. There's no crumple zone. As soon as it's in contact, boom, big force for a shorter time to achieve the same change in momentum. Thus it penetrated further. Yeah?
So if the lead side of the sharpened pencil was also wood as the rest of the pencil, because of the shape of that end, you would actually go a little bit further than the unsharpened?
So if the sharpened pencil, this was all wood, would it go further? If this was really rigid, it wouldn't crumple. And it probably would penetrate a little further. But it's acting as a crumple zone like an airbag in this case.
What about, you talked about simple machines, so it's kind of like a wedge. Doesn't that also increase the time?
Yes, simple machine. This is a wedge, and it's pushing it out. But to exert the same amount of work on the wood, it has to go a farther distance, right? And so that it takes longer to do that over a little longer distance here than here.
So my point is, if it's rigid, wouldn't it still take longer?
Oh, if it's rigid, it would still take... I've never done the experiment, so I don't know. There's other factors going on which we'll study in the next chapter, Pascal's principle. The area affects it too. But again, the dominating factor is that time. And I thought it would be a good example and fun way to review. So, exam 2 Wednesday. Contact me or email me if you think of other questions. Yes? Will I be doing the online retake again? Yes. If you take the exam, you can retake it. If you don't take the original exam, you don't get to retake it. If you choose not to retake it, you get the score you got on exam day. If you choose to take it, I average the two scores. You can bring one-page notes again like the first test. It'll be like it, multiple choice. You can still have one side of an 8.5 by 11 sheet of notes.